Alright, so we were talking about comets in the last segment. Alright, I gotta pick up the speed here a little bit. Alright, so remember, this is just an introductory, chapter 1 is just basically an introductory chapter. So we'll go much more into detail with this stuff as the semester goes on. I know I keep saying that. Alright, so let's see, so yeah, all right. So you know, it's stars, of course, have lots of material around them, not just planets. Anything that is in orbit around the star, is part of that particular star's solar system. I guess I should mention this as well. Within our own galaxy, the Milky Way, as it's called, the spiral galaxy that is our Milky Way, and as I mentioned before, is 100,000 light years from one end to the other, the diameter anyway of the Milky Way. About half the stars, almost half the stars, are actually double stars, binary systems, two stars orbiting each other, and many of those have lots and lots of planets around them. As technology gets better and better, we're finding more and more planets. But our sun is by itself. It's not it's just one star by itself with its system of planets. Jupiter's actually not anywhere near large enough for it to become a star. If the mass of Jupiter had been about a little more than 100 times what it is currently, after all the material accumulated to form Jupiter. If it was about 100 times more mass than it currently has, it would have turned into a star. But again, it's nowhere near that right now, or ever was. Within our galaxy, and in other galaxies as well, but within our galaxy, we see what are called nebula. And nebula just means kind of a cloudy region. Some nebulas are star-forming regions. For example, if you look at the very famous constellation Orion, within just below the belt of Orion, there's a region where called the Orion Nebula, where there's currently star formation taking place. That's just one of them. So these nebulas are generally have lots of gas and dust. And so a lot of them, they're not all star-forming regions, but a lot of them are. All right, so this is a nice picture. This is actually Andromeda, our neighbor. It's actually bigger than the Milky Way. This is one of the designations, M31, Messier Object 31, that happens to be in a galaxy. Just to give you a little mention, that there's lots of different designations for objects in the night sky. This was one of the first designations. There was a guy a couple of 100 years ago named Charles Messier that was actually hunting for comets. And of course, when you're looking for comets, you look for movement, and these objects that didn't move over the course of with respect to the background of stars, we got to talk about that a little bit more. But these things were in the same place night after night after night, and so they were obviously not comets. He didn't really know what they were, so he called them nebula. And he named them. There's about in his original catalog, there's a little more than 100 nebula. And I guess I should mention as well, this bright object right here is a foreground star that's actually within our galaxy. There's actually another galaxy down here, sometimes called not sometimes, it's called Triangulum. Not that matters. Remember, we're studying the solar systems. If you ever want to, by the way, the next semester, the 102, which you guys will already have the book for that as well. If you want to take 2 semesters, you're certainly welcome to, and that will talk more about stars and galaxies. I'm just giving a very, very brief introduction to that. And of course, it'll talk about the universe as well, and what's called cosmology, the actual study of the universe, the study of the Big Bang. All right, so just mentioning the Big Bang, of course, that's our theory, which it's an idea that has had, there's been lots and lots of experiments that we've conducted that supports that theory very, very strongly, that the universe, about 14, just under 14, about 13.8 billion years ago, formed, began, and we don't know what happened before the universe began. That there's lots of speculation about that, but we really have no evidence. There's no data. There's no experiments that we can perform, at least certainly not now. But so anyhow, the universe does have a beginning. It was roughly 13.8 billion years ago, and it's been expanding ever since then. We learned that the universe was expanding less than 100 years ago, in fact, and we're finding out more and more about the universe as time goes on, and as technology gets better and better. You probably heard of this, the Hubble Space Telescope. That object, which has been in space for more than 25 years, has given us most of our information about the universe. Well, I shouldn't say most of it, but an incredible amount of information about our universe that we didn't know before. And hopefully soon, within the next few years, they'll send up, or maybe when you're listening to this, they've already sent it up, what's called the James Webb Space Telescope, the next generation of space telescopes that will be much more powerful than the Hubble Space Telescope, and give us a lot more information. So, all right. So the universe began, like I said, 13.8 billion. I'm going to give you a very brief introduction to this. In an event that we now call the Big Bang, we actually have evidence, experimental evidence of this event that happened. We know how long ago it happened. The universe has been expanding ever since. Stars, shortly after, shortly means, basically a few, at least a million years after the Big Bang, probably less time than that, began to form, and galaxies formed. Galaxies, of course, are huge collections of stars. There's a nice artist rendition of a galaxy. Not all galaxies are spiral galaxies like our Milky Way. Some are what are called elliptical galaxies, generally much bigger than spiral galaxies. And there are some really tiny galaxies that don't have an overall shape, called irregular galaxies. Getting to this idea that stars are born, they go through their life cycle, and then they die. And actually, it's the death of stars that is responsible for us being here. So to kind of answer this question, long billions upon billions of years ago, there were stars that well before our sun existed, which our sun is about 4.5 to 5 billion years old. But long before that, there were other stars, much more massive than the sun, that died in a giant explosion called a supernova. And when that happens, remember how I mentioned before that our sun is turning hydrogen into helium. That's what it's going to do most of its existence, most of its 10 billion year existence, and really only towards the end of its life it'll start making the heavier elements. These really massive stars, about 8 times the mass of the sun or greater, will die in a huge explosion, and in the very instant of that explosion, they're basically creating the rest of the periodic table, all the way to uranium. element 92. All right, so these are that's all the heavy stuff like iron and the things that like calcium, the things that you could think of when you think of the animals and plants and things like that. Carbon, all that kind of stuff was created during supernova explosions. And the supernova explosion seed, that material goes out because it's an explosion that goes out into the rest of the universe and the rest of the galaxy, whatever that local galaxy happens to be, and will seed the next generation of stars. And so when our star was formed, there was lots of material from some distant, some ancient supernova, and so that's why there's heavier elements that were around to form things like the sun and the moon and the Earth, of course. And all right, let's see. So again, the reason that we used light years in, so I'm talking about this next subject here. The reason that we use light years, first of all, things out in space are incredibly distant. Even within our solar system, things are very distant. But when you talk about other stars, you're talking about the light takes literally years, many years to travel from one place to another within our galaxy. So when we look out, for example, roughly the most distant things that we can see are just under 14 billion light years away. That's because that's the age of the universe. That's one of the reasons that we know this. So if we looked at a galaxy, let's say, where the light has been traveling for 12 billion years, this is the nice thing about using light years. You're talking about a unit of distance, but you're also talking about a unit of time. A photon, which is a particle of light, or a wave of light, if you will, took from that particular galaxy 12 billion years to travel that distance. So that's why it's 12 billion light years. Here's a galaxy that's only 7 billion light years away, and so it took that light 7 billion years to reach our telescopes, so that we could record that information. So here's some distances. This is actually the speed of light. It's generally we don't use it. We don't use the value in kilometers per second, but that's it. 300,000 kilometers per second. It's generally in the sciences we use 3 times 10 to the 8th meters per second. So it's that's the speed of light that's been measured for a long time. Actually, it was an astronomer that measured that first. All right, so the moon is just over 1 light second away. The sun, the light that we receive from the sun has traveled for about 8.3 years. A very bright star in the night sky called Sirius, it takes the light about 8 years to reach us. And then, of course, I mentioned this before, the Andromeda Galaxy, the nearest large galaxy to the Milky Way, is 2.5 million light years away. So the further something is away from us, the further back in time that we're talking about. So we can never see the sun as it is right now. We always see it 8 minutes away. The same thing with the stars. The further away the stars are, the longer ago, the longer amount of time that the light left that object. All right, so there's the definition of light. It's the distance that light travels, traveling at 3 times 10 to the 8th meters in 1 second. So this is giving you this is just roughly what the distance is in kilometers, about 10 trillion, 10 times 10 to the 12th kilometers away, about 6 trillion miles. All right, let me pause this and I will start with the next one.